All right, let's kick off section 15.2. We're going to be discussing the concept of line integrals. We're already familiar with integrating over an interval on an axis, that's a single variable integral, over a region in the plane, which is working with double integrals, and then, of course, over a solid in three space, which is triple integrals. We're going to pare it back down to a single integral, but now instead of integrating over just an interval on the x-axis, which is what we're used to, we'd like to integrate over a line or a curve. And so we see in this schematic here under the note, we're starting with a curve, and I'm just going to highlight that base curve here is the lower one that I'm highlighting in green. So that curve is called C. And we'd like to integrate a function over that curve C. And so you can see what this picture is doing is it's segmenting this line up into individual pieces. And you can see in the second picture, it's breaking it up at P1, P2, P3, all the way until it gets to the end of that curve segment. And then it's bringing up what looks very similar to those Riemann rectangles that we saw back when we learned about Riemann sums. And so what we're doing is we're taking this approximation, and then of course we add it all up with an integral. That's why the integral symbol looks like an elongated S, because it's really just an underlying sum. And that's how we're going to compute these line integrals over curves if we look at it schematically here. So let's take a look at a definition of what a line integral really is mathematically. So we're going to start with F, which is a continuous vector field, and C is a smooth oriented curve. Okay, again, oriented just means that it has a set direction, whose parameterization is given by R. All right, then the line integral of F along C is denoted by this integral with the subscript C, meaning we're integrating along the curve C of F dot dr. Now, let me stop right here. Half of the battle when you're learning new mathematics is really unraveling the notation. And so I'm looking at this integrand, f dot dr, and I'm going to say, all right, I know what the dot product is. I know how to take the dot product of two vectors. I've never seen the dot product between a vector field and a differential. So what does this mean, right? So we're going to break it down here. It says, in particular, if f is the function that inputs a coordinate point x, y in two space, and then you can think of it as two component functions. Remember, this is a vector field, so it inputs a point and it outputs a vector. And if r is a parameterization here, x of t, y of t, then what we want to do is we want to take r and we want to plug it into our vector field f. So you'll notice we have f of r of t. And then dr, not surprisingly, the d there generally represents a derivative. So we're going to take the derivative of r, but what is r a function of? It's a function of t. So when I take its derivative there, I'm going to indicate that I took its derivative with respect to t. So what began looking like an integral in terms of r is really just an integral in terms of t, which is our underlying parameter. And so then this next line here is just really spelling it out. What does it mean to take f of r of t? We're just evaluating each of those component functions, little f and little g, at x of t and y of t. Of course, we know what the derivative of the parameterization r looks like, and then we have our differential dt. So this definition was written out assuming that you're working in two space. Of course, if you have one more dimension, we're just going to add those extra components there. So your function will look like f of x, y, z equals f of x, y, g of x, y, f of x, y, z, g of x, y, z, and then h of x, y, z. So we'll have that third component function and similar for r of t. So let's look at an example here of computing one of these line integrals. I want to evaluate the line integral over C of f dot dr along the line segment from P to Q. So they gave us our vector field F. Again, remember that inputs a point in the plane and it outputs a vector in the plane. And then we have a line segment. So for this problem, we don't explicitly have our function r of t. We don't have that parameterization, but we can easily recover it ourselves. So what I'm going to do is I would like to find, I would like to find the vector pq. All right, and now if you'll recall back to when we learned about vectors, you always want to take the component from q and subtract off the component from p. So I have 6 minus a negative 1 and 0 minus 0. Whoops. And so my vector here is 7, 0. All right, so this is my vector. Typically, we wrote this as AB, and then choose which point you want to work with. Since they said from P to Q, I'm going to assume that P is my starting point. And typically, we denoted this by X naught, Y naught. And so then now we need to remember, how do we write a line segment parametrically? And so what we did is we would say that our X component is X naught plus AT. Our Y component was Y naught plus BT. And so using the information that we have, I have -1 plus 7t and 0 plus 0t. So just 0 in the Y component. Since we want a line segment, I need to restrict my t. And so I'm going to restrict t from 0 to 1. I'm going to choose this because I use my starting point P. And so if I plug in 0 for T, I'm starting at P. And you can just check that. You can verify if I plug in 1 for T, or excuse me, 0 for T, X gives me -1, Y gives me 0. If I plug in 1 for T, then X gives me 6, Y gives me 0. So this is the correct parameterization. And then if you want to write it in that parametrization format, you would just input there the X and Y components. So this would look like -1 plus 7t and 0. All right, so what we have now is we have our vector field F, we have our parameterization R, and now we can get started setting up our line integral. We want to compute the integral over C of F dot dr. All right, and what that's going to be is we're going to use our restrictions on our parameter t for our limits of integration, so 0 to 1. Next, I want to plug in my parametric functions into my vector field. And so I'm going to take this component for x, and I'm going to plug that in wherever I see an x. So in this case right here, and then let me grab a different color. Wherever I see a y, I'm going to plug in 0. All right, so let's plug these in here. What I'm going to get is the vector -8x becomes a -8 times -1 plus 7t. And then I have 3 times y, which is 3 times 0. So again, everything that I've written in the angle brackets is f of r of t. I want to dot this with the derivative of r. So since these are linear, when I take the derivative of the x component is 7, the derivative of 0 is 0, and then I'm integrating with respect to t. So I have my single variable integral set up. It almost looks like a single variable integral that we're used to, except for we need to carry out the dot product. But before I do that, let me go ahead and just distribute this 8. I have 8 minus 56t, comma 0, dotted with 7, comma 0. All right, so if I carry out the dot product here, what I'm getting is 56 minus, oh goodness, 56 times 7, 42, carry the 4, 392. So 392. And we have a t. And then of course, the second portion of the dot product is just 0. And then my differential dt. So now we're up to an integral that looks like something that we learned from Calc 1. We can just integrate directly. This becomes 56t minus, now I need 392 divided by 2. So that's 1 and 9. And 196, all right. So then I have a 196t squared, all of this going from 0 to 1. And so then apply the fundamental theorem of calculus, we get 56 minus 196. Of course, the other term would just be 0. And so we get a final answer of -140. So again, really the key to these problems is unraveling that notation. What does f dot dr mean? What I think is most helpful is you remember, you always want to get down to an integral in terms of t. So if you just tried to stick f in, That's no good because f has x's and y's, which makes sense then why we need to plug in r of t to get it all down to that parameter t. All right, let's move on to the next page. The following remark here is just talking about the different ways that you could compute line integrals. And so for the first one here, we have arc length. So what I want to emphasize here is look at this differential. If you see a ds differential, that indicates that you're finding a line integral over arc length. And so what does this mean? All right, so first of all, I know that d is synonymous with derivative, and s is synonymous with arc length. And emphasis on the word length, right? So what I'm going to do is I'm going to take my original integrand f, and remember, I always want to get it back in terms of t. So I'm going to do exactly what I did in the last example. I'm going to evaluate f at those component functions of r, x of t, y of t, and z of t. And then we had the d for derivative, means I want to take the derivative of r, and then the s was arc length. So you'll notice what this is. This is just the length of the derivative. In other words, the magnitude. And then once you've added in that extra factor, of course, you're integrating with respect to t. So I just want to point out that that ds translates into the length of the derivative. Everything else is as before. Again, limits of integration are a to b, whatever those restrictions are on your parameter. We could also integrate with respect to just a single variable. So instead of looking at every variable, let's suppose we just want to do the line integral with respect to z. Again, d is derivative, z is the z component. So you'll notice we just added the derivative of the z component at the end. Again, always integrating with respect to t. I wrote the single variable in terms of z, but a similar definition holds for dx and dy. And then finally, there might be instances where we want to integrate a line integral with respect to multiple variables. So you'll see I have one function that with a dx attached to it, another function with a dy. Again, you want to evaluate each of these functions at x of t and y of t to get them all in terms of t. And then whatever differential you have, whether it's dx, dy, or dz, you're going to tack on the appropriate derivative. And then everything is being integrated with respect to t. So this multiple integral or multiple variables was written in terms of 2 dimensions, but similarly for 3. All right, so let's practice one of these types of integrals. I want to evaluate the line integral. Here, I'll just emphasize that we're working with arc length in this one. So if I scroll back up to the top there, we need to make sure that we find the length of the derivative. So that's the one extra piece of information we need to find here. All right, so in this case, they actually gave us the parameterization. They wrote it out in parametric equations rather than a vector equation. If you want to, you're welcome to write out the vector equation. You would just write your x component first, followed by your y component. And then using this, we can find the derivative. So r prime of t would then be 2, 1. It just becomes a constant function. And then I can find the magnitude. So the length of r prime of t, just using the distance formula, is the square root of 2 squared plus 1 squared. And of course, that's the square root of 5. So this is going to become that extra factor there that I'm tacking in at the end due to the ds. The other piece of information I need to remember is to plug in x and y into the integrand, right? Because we want our entire integral to be written in terms of t. So my limits of integration will always be provided. In this case, we're going from 0 to 1. My numerator x is going to become a 1 plus 2t. My denominator 1 plus y squared becomes a 1 plus t squared. Don't forget that factor of the square root of 5 there. That comes from that ds differential, that arc length. And then, of course, we're integrating with respect to t. All right, so now the question becomes, how the heck do I integrate this? At first glance, I'd want to use a u substitution for the denominator, right? 1 plus t squared is my likely choice for a u substitution. But if I take the derivative of 1 plus t squared, it gives me a 2t dt. And I do see a 2t on top, but I also have that 1 tacked on, which is frustrating. So I can't do a u substitution as this is written. So what I'm going to do is the following. First things first, I'm going to kick this square root of 5 out front because it's a constant. And then what I'm going to do is I'm going to separate this fraction into two smaller fractions. Namely, I'm going to distribute the denominator to the 1, but then I'll also distribute the denominator to the t. And so I'm going to separate this from one fraction to two fractions. So let's see what we have here. I have the integral of, or the square root of 5. And then I have the integral from 0 to 1 of 1 over 1 plus t squared. So there's my first one. And then my second one is 2t over 1 plus t squared dt. Now I put these giant parentheses here so that I don't forget that that square root of 5 goes to both of those integrals. We had talked about actually this second integral is now going to be solved via u substitution. So I'm going to let u be the denominator. Du is just going to be a 2t dt. And I'm in good shape here because now I can just do a direct u substitution. You guys probably know by this time that I'm a big fan of changing my limits of integration if it's easy to do. So when t is 0, u becomes 1. And when t is 1, u becomes 2. All right, so let me write that here. I have my square root of 5. I'm going to come back to this other integral. And then what we just did is we said we can rewrite this as the integral from 1 to 2 of 1 over u du. And this looks much simpler now to integrate. So now let's look back here at this first integral. All right, we can't use a u substitution, but this should be something that you look at and you recognize, yes, I know what this integral is. All right, this is just a direct integration and this is tangent inverse. So this is something that I'll assume my students know just by inspection here, looking at it and recognizing that it's a tangent inverse function. All right, so now we're able to move forward. I'm going to recopy my square root of 5, and then I have the tangent inverse of 1 minus the tangent inverse of 0, and we'll work those out here in a moment. And then next, I get the natural log of the absolute value of u, where u is ranging from 1 to 2. All right, now I know that the natural log of 1 is 0, so I'm going to cross that out. All we're going to get there is a natural log of 2. And so then let's take a look here at these tangent functions. What is tangent inverse of 1? So you need to ask yourself, what radian value from 0 to pi gives me a tangent of 1? And so that happens at pi over 4 because the sine and cosine value are equal. Namely, they're equal to root 2 over 2. And so what I get here is square root of 5 times pi fourths. And then what is tangent of 0? Again, what radian value gives you a tangent value of 0? And that occurs at 0. So I want to go here at 0. And then we already discussed this is going to be natural log of 2 minus 0. You'll notice I dropped those absolute values since 2 is already positive. And so for my final answer, I'll leave it as the square root of 5 times pi over 4 plus the natural log of 2. All right, so that was an example of computing a line integral via arc length. All right, let's do another example of computing a line integral with respect to a single variable. All right, and so in problem 30, we're going to work with integrating with respect to x, y, and z, right? We see all three of those differentials. All right, so two things here. One, we need to remember to evaluate each of these component functions at x, y, and z. Whoops, right over here. And then for each of those differentials, we need to tack on the derivative of each of those component functions. So let me just clean this up here. All right, and let's get started. First, I know my limits of integration. Those are always given. So that's the one nice thing about line integrals. You don't have to think too hard about your limits of integration. Next, let me plug in sine x, or excuse me, sine of t for x. So that becomes a sine squared t. And then what is my dx? It's the derivative of the x function. So the derivative of sine of t is cosine of t. And at this point, you can write a dt if you want, but I'm just going to move on to the next part, and I'm going to write this as one giant integral rather than three individual integrals. So now I'm moving on to the xy. So x is sine of t, y is cosine of t, and then I want dy. So the derivative of cosine is a negative sine. And finally, moving on to the last piece, z squared is t squared squared. So that's t to the fourth. And I want to multiply by dz, which is the derivative of t squared, or 2t. All right, so here is my line integral at face value, just plugging in everything to start. Now we need to see if we can simplify. And sure enough, we can. What you'll see here, and maybe I'll just write it out, even though you might already see the cancellation. I have a sine squared t cosine t. Then I have a minus sine squared t cosine t. And finally, a 2t to the fifth dt. So I have this nice cancellation between my first and second term. And all I need to do now is integrate 2t to the fifth. So that's going to be 2t to the sixth over 6, or in other words, 1/3 t to the sixth. And then I just need to evaluate via the fundamental theorem of calculus from 0 to pi halves. So of course, plugging in 0 gives me nothing. I get 1/3 pi over 2 to the sixth power. You can leave it right like this, or if you want to expand, this is going to be pi to the sixth. What's 2 to the sixth? 2, 4, 8, 16, 32, 64. And what is 64 times 3? 12, carry the 1, 18, 192. All right, pi to the sixth over 192. All right. So far, so good. And so we finish off these notes here by giving an application of, well, why the heck should you care about line integrals? Line integrals are most commonly used in the sciences in physics when you're computing work done. And so we have a definition here. Suppose that under an influence of a continuous force field F, a particle moves along a smooth curve C, and that C, that curve, is oriented in the direction of motion of the particle. Then the work performed by the force field on the particle is given by work equals the line integral over C of F dot dr. So it's that exact same equation that we started out with. Now we're just seeing how it can be used as an application. All right, so for our final example, find the work done by the force field F on the particle that moves along the curve C. All right, so we have our vector field F, and then we have a parabola given by x equals y squared, and we only want part of that parabola from the origin 0, 0 to the point 1, 1. So something that's distinctly different about this problem is we don't have our parameterization R. That is an extra task that we have to take upon ourselves to identify how can I take this parabola and how can I write it parametrically. So what I'm going to do is I'm going to say, all right, it looks like x is the dependent variable and y is the independent variable, which is different than what we're used to. So I'm going to call y t. All right, now that seems silly at first. It's like, okay, well, you're just trading variables here. All right, but bear with me. So if y is t, then x becomes t squared, right? Because if I plug in t for y, that's what I get back out. And so using this, let me write up my parameterization. I can think of that parabola x equals y squared as the parameterization r of t equals t squared comma t. And then furthermore, how do I identify my restrictions? So what I want to travel from is from 0, 0 to 1, 1. So that tells me that I want t to begin at 0, and then I want to go up to 1, 1. Okay, so t goes from 0 to 1. And then let me go ahead and just compute my derivative while I'm at it. that derivative is going to be 2t comma 1. All right, so we have now taken a rectangular equation for a parabola and we've rewritten it parametrically just by introducing that parameter t. And now I can carry out my work. All right, so work is the line integral, but we just said that those limits of integration are going to be from 0 to 1. I want to take my function f, which I'm highlighting up above, and then I want to evaluate it at the x and y component functions. So first I have x, which is t squared, times y, which is t. And then I want plus, oh, and excuse me, let me actually write this as a vector. So let's correct that. Let me use the angle brackets. And then comma, the j hat component is x squared, which is t squared squared. And then dot dr, remember I want to dot it with the derivative r prime of t. So 2t comma 1. And of course, as always, we want to integrate with respect to t. All right, so I have a t cubed times a 2t gives me a 2t to the 4th. And I have t to the 4th times 1 gives me a t to the 4th. Integrated with respect to t. And boy, they were nice to us here. We're just integrating 3t to the 4th dt. All right, I feel really confident in doing this integration. This is 3/5 t to the 5th. I want to evaluate from 0 to 1. And so that gives me a final work amount of 3/5 units. All right, thanks for tuning in.